And thank you for giving me the opportunity to be here. And I have known you for almost a decade now, so it's a pleasure being in Brno. And I'd also like to thank Božena Šekhalova, if I hopefully got it right, for helping me organize this lectures. And so the goal for today and tomorrow is to give a broad overview of a few of the aspects that one can do with in situ microscopy. And I'm biased towards microscopy. For a long time, I've been fascinated with movies, and that's why I like to see as things are happening. And as I tell the students, I'd like to look while I cook. And so that's the whole point of this talk, is to study different kinds of phenomena. And I'll go through the list of things that I will be presenting. And feel free to stop me and ask me questions, or as Professor Shikola said, I'm here either in the building A02 or in SciTech. So you can find me and talk to me, or you can email me. My email address is here. Okay, so first things, and the most important things from my point of view, because none of this research would have been possible since 2007 when I joined as a faculty at University of California, Los Angeles, is partly and greatly due to the Air Force Office of Scientific Research. My program manager is Dr. Ali Sayer, and he has been sustained funding for me throughout these years. And I've also benefited greatly throughout my career as a faculty from funding from a variety of agencies, including Office of Naval Research and National Science Foundation, and my institute, UCLA. All the work that I'm going to be presenting is basically the work that I've done since I was a graduate student. And so I'm greatly indebted to my advisors, my colleagues, my coworkers, and collaborators. I'm only listing here a few, but inevitably over the past 24 years, I have had numerous collaborations, interactions with a lot of them, and I cannot list all of them. So I'm thankful to my advisors, PhD advisors, Professors Joe Green and Ivan Petrov at University of Illinois, Urbana-Champaign, during which time I had the pleasure and fortune to collaborate with a postdoctoral research scholar at that time, Professor Sanjay Khare, who is now the head of the Department of Physics at University of Toledo. And all my high temperature STM and low energy electron microscopy results that I'm going to be presenting now that were done at University of Illinois are greatly thanks to Ms. Vanya Petrova, who's in charge of the STM facility at the Materials Research Lab, pretty much like the SciTech here, and the Dr. Vaclav Struyok, who happened to work with the inventor of LEEM, Professor Ernst Bauer. And so he was in charge, Watzek was in charge of the LEEM facility in the Materials Research Lab at University of Illinois. And as part of my postdoc, I benefited from my postdoctoral advisor, Dr. Francis Ross, who is now the faculty, is a professor in MIT, and Dr. Jerry Tursoff, who's still at the IBM T.J. Watson Research Center. After joining UCLA, I had the pleasure of collaborating with Dr. Kevin McCarty and Norm Bartelt, who are staff scientists, or who were staff scientists at Sandia National Labs, Livermore. And in some of the results that I'm going to be presenting on nanomechanics are done by Dr. Jeff Wheeler, who's a staff scientist at ETH Zurich. And over the last 14 years, I have had great collaborations with my good friend, Professor Christian Ciobanu, who's a professor in Department of Mechanical Engineering at Colorado School of Mines. So the lecture are divided into two parts. And in this lecture, in today's lecture, I will give an overview of the in situ scanning tunneling microscopy and low energy electron microscopy as tools to study surface dynamics, the phenomena that would occur on surfaces at near equilibrium conditions. and also the growth kinetics, where I will present results from our work on two-dimensional layers and how they grow. And in this sense, I will choose graphene and hexagonal boron nitride, and I'll showcase a few results from those. All my surface dynamics experiments were done as a graduate student and 2 years of postdoc while I was at University of Illinois. All the graphene and hexagonal boron nitride work is done while after joining UCLA. And tomorrow, I'll continue with the same in situ microscopy as the theme, but I will focus more on electron microscopy techniques, the transmission electron microscopy and scanning electron microscopy for studies of nanowire nucleation and growth kinetics and nanomechanics. And the nanowire growth kinetics work is mostly done at IBM T.J. Watson Research Center. If I have time, I'll showcase a slide or two on the more recent nanowire etching kinetics that were done while I was on sabbatical at Lund University. And all the in-situ SEM is done mainly at UCLA and also at ETH Zurich. And all of my work over the past since graduate school have benefited mainly from some of the pioneers in this field. And I'm listing a few whose work I have followed and copied and tried to implement it into the material system that I was working on at the time. And in that sense, when I started as a graduate student, I came across very interesting and very elegant papers from Professor George Kamsa's group while he was a faculty or staff scientist at Jülich Research Center. And at that time, I guess his group consisted of Professors Margaret Geeson, Karina Morgenstern, and Basenbacher, who all of them now have faculty appointments at different places, and also Professor Thomas Micheli, who I think some of you may know. And during the same time, I've the crystal nucleation and growth kinetics, which is mainly the theme of most of my experimental work. I benefited greatly from reading papers from Jerry Tursoff, Norm Bartelt, and Ruth Tromp. Jerry Tursoff and Ruth Tromp are staff scientists at IBM T.J. Watson Research Center, and Norm Bartelt is a staff scientist at Sandia National Labs, Livermore, and Professor Ellen Williams, who used to be at the University of Maryland. And they have done pioneering work on surface dynamics, surface crystal growth, and the surface step fluctuations, and you will see the work that is derived from their work in my talk. And most important aspect, please do not be offended if you do not see the references that belong to you or that you think should have been here. And this is not by choice that I have not listed all the references. It's mainly because I'm presenting my work and compiling all the literature related to what I've done. It will become a review by itself, and I have not done that. And most of the references are probably outdated, especially for graphene related work. But I think I try to present them in what I think, especially the really old literature that I give you here, are timeless. Okay, let's come to the main theme of the talk. And so in the first half an hour or so, I will present results on surface dynamics phenomena. And in this, and to showcase the phenomena of surface dynamics, I will be presenting results. All of them are obtained from titanium nitride. And I will present a few results from scanning tunneling microscopy and low energy electron microscopy. Using these techniques, the idea is to study the dynamics occurring on surfaces and to be able to quantify the observed phenomena. Okay. For those of you that are not familiar with titanium nitride, it belongs to this group, early group transition metal nitrides, which are hard, refractory, and are used in a variety of hard protective coating applications as cutting tools and even as diffusion barriers. And in case you have come across cutlery or decorative objects that look like gold, but it's not gold, that's most likely titanium nitride. These materials are used in a very advanced structural applications. And for most of the applications, industry prefers to deposit them as thin films or coatings at low temperatures compared to their bulk melting points. And so typically the microstructure that one obtains is far from equilibrium, and their properties at that time were not well known. And so we have chosen titanium nitride as a model material that has been used in a variety of these applications, and try to focus on surface morphological evolution as a means to understand how atoms move on surfaces, how they assemble to form a given crystal structure. The studies that we have done, and I will showcase to you, are a few of the examples are shown here. I hope you can see my cursor. So one of the phenomena that I'll touch upon is the island coarsening kinetics, or the kinetics of Ostwald ripening. And I will touch upon the idea of fluctuations within a given shape and how one can analyze the fluctuations to extract one of the important parameters, the step formation energies, which is a 1D or 2-dimensional analog of surface free energy. And from these types of measurements, we can determine the equilibrium crystal shape for a 2-dimensional island and use that information to get the anisotropy in step energies. And the other phenomena I'll touch upon in a few slides is the phenomenon of island coalescence, where 2 or more clusters can come together and form one large island, which eventually will reshape itself into what would be the equilibrium shape at that given temperature. So the experiments we did is to first deposit epitaxial titanium nitride thin film on single crystal MgO substrate, and all the images you will see will be titanium nitride surfaces. And the 2 orientations we have studied are titanium nitride 111 films that were grown on either MgO 111 or on Sapphire 0001, or titanium nitride 001 oriented films that are heteroepitaxially grown on MgO 001. And what you'll be seeing here in the next slide is a scanning tunneling microscopy image and time-lapsed images obtained over a period of roughly 2.5 hours while annealing the sample at about 850 degrees Celsius. This is roughly the 1/3 of the melting point of titanium nitride. And in this particular experiment, the titanium nitride islands were deposited on top of the titanium nitride surface, and the island coverage is about 0.15 monolayers. And the field of view is about 1 micron, and this is about 800 nanometers. 100 nanometers and 83 nanometers this way. Okay. And I want you to pay attention to a few of the aspects that I've highlighted here. So you will see step fluctuations of different types of steps, and you will see that some of the steps will fluctuate more than the others. You will see the disappearance of islands, and you will see phenomena of coalescence. Okay. So this is a time-lapsed STM images that are compiled together as a movie. And this is obtained while scanning the sample at 850 degrees Celsius in the STM. And so as time progresses, you probably have seen a lot of these smaller islands disappear. Some of the larger islands coalesced, and you will see these fluctuations in these step edges, whereas the fluctuations are more at certain oriented step edges compared to the other steps. Okay. And I'll talk about how to use this information to extract fundamental parameters pertaining to this system. Okay, first, let me focus on the phenomenon of Ostwald ripening. And here is a snapshot of similar experiments that were done at slightly about the same temperature, 890 degrees C. And this is as time progresses. Initially, you start out with a large ensemble of islands, 2-dimensional islands. And I should mention that these are all titanium nitride steps. And these steps are single atom height steps and on an otherwise atomically flat terraces. And you see a few large islands and a lot of small islands. And I just want to focus your attention to this cluster of islands around this large cluster as highlighted here. And as time progresses, you see that most of these smaller islands have disappeared. And if you take the islands situated on top of the larger terraces, these islands labeled A and B, as time progresses, the island B seems to be about the same size, whereas the island A has disappeared. And I'll talk about those aspects of how or why this phenomena would come about. So as what you have seen is a classic example of Ostwald ripening. It's a phenomena where large clusters grow at the expense of small clusters. Now, you may have heard of, a good example for that that you're all probably familiar with is soap bubbles in water or oil droplets inside water. If you wait long enough, all the smaller droplets will disappear and you will end up with the one larger droplet. And the rationale behind this phenomena is that the vapor pressure associated with a given size of a cluster or a three-dimensional object is exponentially related to its curvature. And it's mathematically given by the Gibbs-Thomson relation, where the atom concentration N associated with a cluster of radius R is exponentially related to the step energy and the curvature of the island. Okay, in this form here, this is assuming that these are circles, and that's why the curvature is written as 1 over R. But to be in the strictest form, this would be written as curvature. Okay? And N0 would correspond to the equilibrium atom concentration associated with a straight step. So ideally, as the time progresses, all these islands will disappear, and eventually you'll end up with only steps. But within a given limited amount of time, you'll always end up with some large clusters and a few smaller clusters. And for this small cluster to disappear and for this large cluster to grow, one can envision 3 different processes that have to happen. One is that the atoms from the small cluster have to detach. They have to either diffuse on the surface or desorb and come back from the vacuum, and then reattach at the larger cluster. And so one can identify which is the rate limiting mechanism in each of these 3 processes, and that was done a long time ago by Lifshitz and Slysov, who came up with the mean field theory model, where assuming that the atom concentration on the surface is uniform, and assuming that the clusters are all circular, they have, and if the clusters are large enough, the exponential could be expressed in terms of the first 2 linear terms, using which they were able to identify how the area of a given cluster would change with time. And the scaling exponent associated with this behavior is indicative of the mechanism that controls this process. If the scaling exponent turns out to be 1, meaning the area of the island scaling linearly with time, that would happen if the attachment or detachment of atoms at the step edges of the cluster is the rate limiting process. If that is the lowest, slowest process, then you would observe the area of the island to change linearly with time. And if the scaling exponent is 2/3, it implies that surface diffusion is the rate limiting step. Okay? So this is the classical mean field theory. But experimentally, typically, when you do these experiments with small size clusters, the mean field theory model fails to explain the observed behavior. And let me tell you why. So this is another experiment. This is, again, these are islands. And from the time-lapsed images, we can measure the areas of these islands. And I've only highlighted 4 of them here. And we can plot the area as a function of the annealing time. And as you can see, for the 4 of these curves, we can use the power law relation, and using which we obtain scaling exponents anywhere between 0.55 and 0.67. These are close to 2/3, but not exactly same as what is expected from the mean field theory model. Okay. And so to explain this quantitatively, we have to do additional experiments or observations. And here is one observation that tells us what is exactly going on the surface. So if you take an ensemble of clusters that are labeled 1 to 5 here, and if we plot the change in island area as a function of time, you will notice some interesting behavior for the blue triangles and also for the red squares. The smaller islands, this island labeled 1, disappears quickly. The other islands, the purple one, which is away from, there's relatively few number of neighbors, that also monotonically decreases in size. However, for island number 4, which is surrounded by other islands, and for island number 5, which is also surrounded by other islands, you notice that as island 2, which is close to island 4, as that decreases in size, there is a corresponding increase in the area. So, which indicates that there is, well, mainly because there is mass conservation, and part of the reason is because as island 2 is decreasing in size, as it's losing atoms, some of the atoms are likely going to these larger steppage, but a few of the atoms are attaching to this other island 4. So even though this island 4 is smaller to start with, it gains some atoms because island 2 starts to lose all the atoms because it's in the vicinity of a straight steppage. The concentration gradient is higher here. Okay. So this type of behavior is characteristic of surface diffusion limited processes. So if diffusion is the limiting step, then you would observe this type of local environment dependent change in the growth or decay kinetics. So now we know that its surface diffusion is the limiting behavior. Now, how do we quantify this behavior and what type of information can we extract from these type of studies? So for that, we prepared carefully designed configuration. So this is a single atom island within a vacancy pit. So this is one step down, and this is one atom high island. And as time progresses, it disappears because it loses atoms to the step edges of this vacancy island. And this is the opposite scenario where there is an atom island on top of a terrace. Okay, so similar thing happens. Here also the atom island disappears in size, but there is a difference between this geometry and this geometry. Here, the atoms that are coming out of this smaller atom island, they simply reattach at this steppage, what I'm going to be calling as the ascending steppage. In this case, the atoms have to jump down the steppage and they have to attach at this steppage. So they have to overcome an additional barrier, the so-called Ehrlich-Schobel barrier. Okay. And I won't go through the details, but we can precisely model the island decay kinetics from the data, and we can quantitatively fit the experimentally observed behavior. And the only two parameters in the model are the surface diffusion parameter and what I'm going to be calling as a step energy parameter B, which is a measure of the step formation energy, and I'll come to it in a few slides. So using the modeling, we can now accurately explain the observed behavior, and from the fits, we can extract the step energy parameter, which turns out to be 0.23 electron volts per angstrom, which is proportional to the step formation energy, but it's not the step formation energy yet. I'll come to how to extract that soon. And from these types of fits, we can extract this parameter at each of the annealing temperatures. And so we can now plot the N sub 0, which is the equilibrium atom concentration, times the surface diffusivity for titanium nitride. And this is the data that's obtained from these fits for different islands. And this is as a function of the annealing temperature. And this is all done by the STM. And the slope of this curve is the activation energy, which corresponds to the energy required to remove an atom from an existing atom island. So that's the atom formation energy, which corresponds to this N sub 0, and the surface diffusion parameter, and so that's the E sub S. So the energy, the total energy we get from this is about 2.6 electron volts. And this is for the atom islands within the vacancy islands. And the same type of experiments that are done for atom islands on top of terraces. So for these ones, they're an extra barrier, and that is the Ehrlich-Schobel barrier for the atoms to jump down the step. And so for that, we get the total activation energy, which is about 3.1 eV, but within the errors of measurements, these are about the same, meaning that the Ehrlich-Schobel barrier for atoms to hop down titanium nitride steps is within the errors of our measurement. So from the island decay measurements, from the size, from the changes in the sizes of islands as a function of annealing time, we can extract the some of the parameters such as the activation barrier for surface diffusion and also the Ehrlich-Schobel barrier. Okay. And we have done similar experiments for titanium nitride on 111 surface, and here because the symmetry is different from the 001, you observe these fairly triangular shaped islands instead of hexagonal shape, and that's because the surface is highly anisotropic. And we can extract similar type of activation energies, and there is some interesting behavior that happens. There is a size-dependent change in the decay behavior, and if you're interested, I can talk to you more about it. Okay, now let me come to another interesting and very important aspect that belongs to surfaces, and that is the step formation energy. And I'm going to be using this term beta, which is a 2D analog of a three-dimensional surface energy, the gamma. And the step energy can be a function of the step orientation phi. And this, if it's completely isotropic, the step energy will be the same for all step orientations. But if it's anisotropic, which is the reason that you see square-shaped islands on 001 surface and triangular-shaped islands on 111 surface, instead of completely circular shape, then the step formation energy will be strongly varying with the step orientation. And in the three-dimensional crystals, you're probably familiar with the so-called Wolf plot. And this is a polar representation of the surface energies as a function of orientation. And one can do the same for two-dimensional islands on surfaces. And one can have a polar representation of the step energies as a function of step orientation. And the Wolf theorem tells us that one can determine the equilibrium island shape from the Wolf plot. Okay, and to do that, but it gives you only the relative changes in this one, and so we need to be able to do quantitatively how to determine the step energies. We're going to do two things, and one is to use the island disappearance rates that I just mentioned about, the Ostwald ripening phenomena. And the other way is to measure the fluctuations that you observe during these island decay process in the island shapes, and use either of them to determine the island chemical potential. And once you have this one, we have absolute step energies as a function of step orientation. And I'll quickly go through this, but if you're interested, I'll be happy to talk to you on this topic. So basically, the equilibrium island shape as a function of orientation can be related to the step energies as a function of step orientation by inverse Legendre transform. And this was done by Nogiers a long time ago. And if you were to do this for two-dimensional islands, the step energy is given by this expression, where R of theta is the shape function of the island of interest, and it's the equilibrium island shape. And lambda is the equilibrium chemical potential per unit area. Okay. Typically, when you do Wolf plots, you get this relation, but without the lambda. And without the lambda, you do not have any absolute values. All you know is how the step energies change with orientation, but not by how much. Okay, so what we do is we first measure the shapes of the islands. And these are time-lapsed images. So from these individual contours obtained over a longer time, we then do an average shape of this, and the average shape of all these types of independent any time shape functions at any given time. You get the time averaged shape. And for 001, as you can see, that the step edges, and in this particular case, it's rotated 45 degrees, and that's why you see these step orientations as written here. And we see the step energy anisotropy, and that is the ratio of the step energy 110 to 100 is basically the ratio of the radial lengths of these steps from the center of mass of the island. Okay. Now, again, as I mentioned before, this is just the relative information, but now we can get the relative change in the step energies, and this is the polar plot, by doing this transformation. And once we have that information, now we need to get the step energy parameter. And to this, we use the island decay behavior. And I'll not go through the details here again, but I'll give you the gist. And that is that from island decay behavior, we get this parameter B, which is actually the step stiffness times the shape function, which is essentially the curvature times the average radius. So all this information is available, the shape function and the step energies parameter, from the island decay measurements. And so we can now obtain the chemical potential of each of the islands. And once we have it, we get the absolute step energies, and here is the data. So the beta, the red curve, shows the actual change in the step formation energies for titanium nitride steps as a function of step orientation. Okay. And the step stiffness also one can calculate once you have step formation energies, and that follows as shown by this black curve. And if you recall the step fluctuations that you saw in the video, the steps that fluctuated more vigorously, those are the steps with low stiffness. You can think of them as guitar strings that are tight versus a bit loose. The ones that are loose vibrate more. This is essentially the same thing. So the steps with low stiffness, they fluctuate more. The steps with high stiffness, they are the stable steps, and they do not fluctuate as much. And so we can get the step formation energies and step stiffnesses. And from the step stiffnesses, we can also extract kink formation energies. But however, these depend on on a particular model that you choose. And so anyway, all this type of information one can obtain by doing scanning tunneling microscopy and watching the dynamics happening on surfaces. You recall that I mentioned that you can also extract step formation energies from measuring the fluctuations in the shape of a given island. And so that we can do it. And the idea is very similar. So the equilibrium shape of the island has the lowest free energy. Any changes in the shape of the island, you increase the free energy. And a change in the free energy is a measure of the magnitude of fluctuations you observe. And this can be quantified. And we have developed a formulation for measuring the chemical potential per unit area as a function of the fluctuation modes and the number of modes you have in a given island. And using those measurements, and again by measuring the equilibrium shapes of the islands, we can now extract step formation energies and step stiffnesses also for any given surface. Okay, and so this type of information is fairly straightforward to obtain once you have experimental measurements. And the scanning tunneling microscopy is a great tool for quantitative description of these types of phenomena. Okay, and quickly I'll go through island coalescence kinetics. It's 36 minutes, okay. And so here you have seen let's see if I play this one. Okay. Well, for whatever reason, it's not playing today, but that's okay. So you have seen this before. So there are two islands come in contact with each other, and they coalesce and form a larger island, which eventually reshapes itself. Now, the theory of surface relaxation was developed by Mullins a long time ago. Actually, this is a relatively new reference, but the theory was developed a long time ago. And it was assumed that any arbitrary shape would evolve into an anisotropic shape, in which case the step velocity is given by the gradient of the curvature. Okay, But for anisotropic islands, where the step energy changes and step stiffness changes with orientation, you cannot simply use this formalism. You have to actually take the chemical potential, which is now a product of step stiffness and curvature, both of which change with orientation. And there is no analytical solution for this because now you have strong variations in both these parameters as a function of orientation. So this has to be modeled. But once you model it, you can now extract quantitative parameters. And this is the activation energy associated with edge diffusion. And the reason is that when the islands coalesce, now this is a far from equilibrium shape. The surface energy for this island is high. And so eventually it relaxes to this equilibrium shape. And typically there are more, the atoms can diffuse along the step edges, or atoms can detach and reattach at the other step edges. And depending on which mechanism contributes to this, you have slightly different rate of change in the island perimeter as a function of time. And by modeling this, we can account for this phenomena. And from the time-dependent change in the shape of the island, we can then extract the activation energy associated with this shape transformation process. Okay, so that summarizes my STM talk on the types of phenomena that one can study using scanning tunneling microscopy observations of island shapes, island sizes as a function of given time. Now let me present a complementary study that's done using a low energy electron microscope. And I know that at SciTech there is one of the new and more advanced LEEM, and it's a great tool. I used one of the first LEEMs. I think this was called IBM LEEM 1. This was made by IBM. It's an IBM old design. And for those of you that are not familiar with this technique, it basically uses very low energy electrons, typically a few electron volts, to image the surface. And because these low energy electrons can get deflected very easily, you typically use a high energy electron source and you direct them onto the sample, and very close to the surface of the sample, you decelerate the electrons by biasing the sample. And you use these low energies, which are then scattered from the surface. And if the sample is crystalline and relatively smooth, then you can observe diffraction from the surface, and you can collect a variety of signals from the electrons deflecting or scattering and diffracting from the surface. Instead of the electrons, you can also use a UV lamp for photoemission electron microscopy. The technique is highly surface sensitive, and unlike scanning tunneling microscope where you scan the tip on the surface, in low energy electron microscope there is no scanning, and so you collect images in real time. And the typical field of view is anywhere between 2 to 10 microns, and the spatial resolution has been improving over the past 2 decades. And typically you can observe subsurface defects, and so that's why I call it sub-angstrom resolution in the Z direction. Laterally, it's anywhere of the order of a few nanometers. And the time resolution for a standalone LEEM is of the order of video rates. But if you can do it on a synchrotron, you can have higher time resolution. And I'll show a few examples of how the LEEM can be useful in studying the surface morphological changes, and even to some extent quantify the chemical changes. And I'm sure some of your colleagues here are doing different types of studies where they're able to follow surface chemical reactions and phase transformations as well. Okay, so for this study, we've chosen titanium nitride 111 and the annealing temperature. So this is being annealed in a positive pressure of nitrogen just to make sure that we don't have any nitrogen desorption from the surface. This is done at about 1300 degrees C. And this field of view is about 4 microns. What you're looking at are these single atom height. Well, technically for titanium nitride 111, it's not a single atom height, it's a bilayer because titanium nitride 111 is a polar surface. So you have individual rows that are made of the same, individual layers made of the same type of atom. So titanium atom layer and a nitrogen atom layer. So each of them is a bilayer of titanium nitride. These darker lines are thick step bunches and grains within these film that was deposited on the sapphire crystal. And what you're looking at here are the decay of these, what I call mounds. So you can think of them in LEEM, you're looking at a two-dimensional projection of a three-dimensional surface. And so these are mounds, something like a wedding cake where you have stack of islands on top of a terrace. And so when we are annealing this, we observe a lot of step motion and the disappearance of these islands and a continuous flow and rearrangement of the surface. As time progresses, the surface eventually gets smoother. So from these types of measurements, we can, again, similar to the STM data, we can measure the areas of these islands as a function of time. And these labels, these are the plot of island areas as a function of time for different islands. And you see here is a fairly linear decay behavior. But there are more details in here that basically the rates at which these islands disappear is one has to model this phenomena. And what we find is that for titanium nitride and in these wedding cake configuration, the atoms can diffuse much faster than overcoming an Ehrlich-Schobel barrier. This phenomena is referred to as step permeability, which is a funny phenomena that's not commonly observed in a lot of materials, but experimentally it has been observed in silicon and I think maybe in copper. And this is the phenomena where atoms can funnel through rather than overcome the barrier. So the decay behavior is significantly enhanced. And so for titanium nitride 111, at these temperatures, we extract an activation barrier of about 2.8 eV for the disappearance of these islands in this wedding cake configuration. Now I'll come to a rather interesting aspect. So often when we grow these thin films, we observe some defects, and this is a screw dislocation that is terminating on the surface. And when we anneal this sample at about half its melting point, okay, we see this screw dislocation, steps around the screw dislocation growing. If you're familiar with the Burton-Cabrera-Frank theory of crystal growth, the so-called BCF theory, the similar phenomena was proposed for the growth of crystals. So when you have deposition occurring at a step edge that's terminating at a screw dislocation, the steps can grow and one can measure the step velocity and understand how the crystals grow. But here I want to point out that what we are observing is not a growth spiral because we are not depositing material. We are not desorbing material from the surface. This temperature is not high enough for titanium or titanium nitride to desorb. And so essentially what we are observing is surface transport and maybe bulk transport, and I'll tell you that in a second. Okay. And so from these measurements of this spiral step motion, we can measure the angular velocity and the time it takes for the spiral to appear to be exactly same as same is about 47 seconds. So it repeats itself. And there is no external stress, there is no deposition, evaporation. And so to explain this behavior, we compare and contrast the rate at which these steps grow and the rate at which these islands disappear. And we find that the spirals grow at a constant frequency and the islands decay at a constant rate. And we can extract the activation barriers associated with the decay of the islands and the growth of the spirals. And we find that the growth of the spirals is associated with a higher activation barrier of about 4.6 eV, whereas for the island decay, it's between 2.8 and 3.1 eV. So basically what it tells us is that the decay of islands is a phenomena that's different from the processes that are controlling the growth of the spirals. And so we then came up with the proposition that the spirals must be nucleating and growing because of the transport of atoms from or to the bulk. And that has been observed in other material systems such as titanium dioxide and also nickel aluminide. And so we expect that because if the surface is nitrogen deficient, maybe the titanium atoms would go down and you could have pipe diffusion, and that controls the rate at which these spirals would grow. Okay, just like a fountain. You can imagine this to be a water fountain or a sink. And so you could form a mound that's growing upwards or a mound that is going inwards. Okay. So hopefully I gave you an overview of the type of surface dynamical phenomena that can be studied using scanning tunneling microscopy at high temperatures, but you can use it at any temperatures that suits your material system, and also using low energy electron microscope. Okay, now I'm going to switch gears and move on to a slightly different topic, and that is the growth of two-dimensional islands and layered materials. Okay, so in the next 30 minutes or so, I will showcase the use of low energy electron microscopy and scanning tunneling microscopy to study orientation property relations in graphene, the growth of graphene and hexagonal boron nitride, and a few slides on some of the work that we did a long time ago, and that is surface chemical reactions that enhance or suppress morphological evolution on titanium dioxide. So I'll start with the TiO2 first, and because that's a bit different from what we have been doing with the 2D layers. And here what we decided to do is to take a single crystal TiO2 and expose it to different environments, either vacuum or oxidizing environment or reducing environment. And for those of you that are familiar with TiO2, rutile TiO2, there is this so-called stripe phase, which leads to a 2x1 reconstruction. And experimentally, you would observe this both in the low energy electron diffraction patterns and also in scanning tunneling microscopy images. These are these stripes that appear. And for TiO2, each of these stripes, once you have a complete layer of these stripes, you recover the 1x1 phase. And again, it repeats itself. So these underlying layers, let me show it to you on the next slide. So here you see the TiO2 surface, and this is a scanning tunneling microscopy image that's obtained while annealing in vacuum at about 900 Kelvin. You see these relatively flat, slightly grayish color islands. These are 1x1 phase. And on top of these 1x1 phase, you have these stripes, and these are the 2x1 phase. And once you have enough 2x1 stripes, you recover the 1x1 surface again. Okay. And without going into lots of experimental details, I'll give you the highlight of these experiments. So these are time-lapsed images that are obtained while annealing the sample at about 900 Kelvin in presence of ethylene. And what we observe is that as time progresses, we see an increase in the growth of the stripe phase. Remember, the surface is TiO2, and we are exposing it to ethylene, but we are observing the growth of TiO2 structures, not carbides. Okay, and so this was puzzling for us for a minute, or well, for a lot of experiments. And then we did a series of experiments as a function of ambient and as a function of temperature and time. And what we observe is that a mixture of ethylene and oxygen with small traces of oxygen significantly enhances the growth of the stripe phase rather than just annealing in pure oxygen at a given temperature. And annealing, of course, in vacuum, you lose the oxygen from the surface, and so the stripe phase decreases if you are annealing in vacuum. And here is the summary of those experiments. So this is the growth rate of the stripe phase, and this is normalized to the dose of a given gas. And here the red symbols correspond to the exposure to oxygen at different temperatures, and the green symbols correspond to the exposure to ethylene. But what is not said here is that it's not pure ethylene, but there is a background, small traces of oxygen as well. So it's ethylene with small traces of oxygen. And what we see, which is counterintuitive, is that the exposing it to ethylene plus oxygen significantly boosts the growth of the stripe phase. Okay? And we proposed some theory to explain why this happens. I'd be happy to talk to you about what we think is happening. Okay, so that's about surface reactions. And again, this is now it's fairly standard to use scanning tunneling microscopy to study catalysis, and some of your colleagues are doing these types of experiments either here or they have done this in the past. And so that's one slide or some information that I wanted to share with you. And now let me come to the use of scanning tunneling microscope at high temperatures for observation of graphene growth. And first we started out with silicon carbide. For those of you that are not familiar with this concept, you take single crystal silicon carbide, and if you heat it in vacuum or in inert atmosphere to high temperatures, carbon stays on the surface, silicon preferentially desorbs, and so you can get graphene, or if you do it for longer times, you will get graphite. And this phenomena was observed a long time ago, and in the recent years, this process has been used and to controllably grow either monolayer graphene or bilayer graphene. There are a lot of studies that have focused on controlling the growth orientation and the quality of graphene on silicon carbide. There are a lot more references than I can cite here, but I've chosen a few that I thought at that time were focused on the growth-related aspects of graphene on silicon carbide. And all these references are point to the use of electron LEEM to study the growth of graphene. What we did is complementary to this to use STM to study this. And one of the interesting and fortuitous aspect that came to our rescue was the surface roughness of the silicon carbide. A carburized silicon carbide is sensitive to the structure of the layer that is formed. So when you do uncontrollable annealing of a silicon-rich silicon carbide, as silicon leaves the surface, you end up with one or more of the following phases. One, the first thing to form is the so-called 6√3 by 6√3 phase in the graphene community. This is also referred to as the buffer layer. And this layer is formed before the growth of monolayer graphene. And if you continue to anneal, you may also end up with bilayer graphene. And it turns out that the surface roughness of each of these phases depends on the phase. So for the 6√3 by 6√3 phase, you have higher roughness than for a bilayer graphene. And this seems to be the same either at room temperature or from the STM images obtained while annealing at 1120 degrees Celsius. It's also about the same. So we use this to follow the growth of bilayer graphene. So this is a representative scanning tunneling microscopy image obtained while annealing at 1120 degrees C. And what you're looking at here as color-coded is you have monolayer graphene covered surface, and the regions that are colored with green are the bilayer graphene. And we watch this surface as a function of annealing time. And what you're going to be looking at is time-lapsed images obtained over 140 minutes. And you see the surface changes. And here the silicon is desorbing from the surface, leading to the formation of the bilayer graphene. And these are the snapshots, and this is for your benefit. I've color-coded the regions so that you can see there is the bilayer graphene, and the bilayer graphene colored increases after 147 minutes, indicating that you have more graphene growth, and we can quantify this process. And so when you plot the areal change, areal coverage of a given layer as a function of time, you see that the graphene coverage increases and the silicon carbide coverage decreases, and the amount of change in silicon carbide is roughly 3 times that of the amount of increase in graphene coverage. And that's what you would expect, that you need 3.15 layers of silicon carbide to form 1 layer of graphene. And we've also looked at the atomistics of how this second layer graphene grows, and I will not go into any of those details, but we observed 3 different modes of graphene growth at the graphene-free silicon carbide steps and at the silicon carbide graphene interface and in front of graphene. And based on these, we've been able to identify a rate-limiting step for how bilayer graphene grows on silicon carbide surfaces. Now let me come to the more common way of graphene growth. And in this sense, I want to recall the literature that is often forgotten by the newer community. So I mentioned before that the silicon carbide graphitization was done a long time ago. Similarly, the graphene growth, at that time they were calling it monolayer graphite, and that was done on metals, borides, carbides, and on nitrides a long time ago, and there is a good review of graphene growth on different surfaces. And the phenomena of carbon segregation and graphene or graphite formation on metals that can dissolve carbon was studied by Jack Hamilton, whose thesis, I think, was one of these materials. And there is studies that talk about surface phase diagrams for carbon on these metals. And if you're also interested, there is a nice review of everything about carbon on transition metal surfaces. And we can see that that's about 200 pages of carbon. So, and in terms of surface science studies, there is nice literature that talks about the different types of substrates, different types of gases and sources that have been used, and characterization techniques for study of monolayer graphite formation. Some of this literature dates back to 1975. And more recently, the silicon graphene growth on silicon carbide was done primarily using LEEM, and graphene growth on metals was also done by LEEM, mostly by Norm Bartelt and Kevin McCarthy's group at Sandia National Labs, Livermore, and by Peter Sutter, who used to be at Brookhaven National Lab and now at University of Nebraska. And the graphene on metals using STM is done mostly in Europe, and one of the notable professors that has worked on this is Thomas Micheli. And our motivation for a study, and for those of you that are familiar with this topic, is that when you grow graphene via using any of the hydrocarbons on typical metals, which is usually polycrystalline, you end up with polycrystalline or polydomain graphene. And this shows, so this is a copper, cold rolled copper, so it has 001 texture. And so when you grow graphene on 001 oriented copper, you end up with these 4-fold symmetric graphene domains. And this is a lean image showing that you have these 4 different domains. And more importantly, people have studied how defects influence either mechanical or electronic properties. And here is one atomistic simulation that show that the type of defects within a 2D layer, in this case graphene, affect the mechanical behavior of the graphene. And electronically as well, depending on the type of defects, you can have perfectly conducting domain boundary or an insulating domain boundary. So the electron transport across these domains depends on the type of defects, type of domains that you have within a monolayer graphene as well. And experimentally, this has been verified too. So basically, all these studies indicate, as you probably know, that the defects are important. One needs to be able to control, and if possible, and if needed, eliminate completely these defects. And other studies have also shown that the properties of 2D layered materials depend on the layer thickness and the layer orientation. And so one needs to understand how these layers grow and how they're oriented and how can we control this orientation. And this, I believe, can only be achieved by fundamental studies focused on how the layers nucleate and grow. And one ideal example that I can think of is the studies that were done by Ru Trump and Jim Hannon at IBM TJ Watson, helped develop methods to obtain single domain graphene across a 3-inch wafer at that time on silicon carbide surface. So they carried out lean studies to identify what happens and how the graphene grows on silicon carbide. And using that information, they developed methods to perfect the growth of graphene layers on silicon carbide. And so I'll first present the use of LEEM for studying structure property relations and for growth kinetics for graphene growth on palladium-111. And for this one, we have been working with palladium for a long time. And it so happens that palladium is an ideal contact for carbon nanotubes and also for graphene. And so it could be good for graphene metal contacts. And palladium, like other similar transition metals, has good solubility for carbon. This is a partial phase diagram of carbon palladium. At the palladium rich side, what you see here is that palladium can dissolve carbon and exist in the face-centered cubic structure at high temperatures. But as you cool down, you have graphite formation. You have a two-phase, which is the palladium with a little bit of carbon in the FCC lattice and graphite. Now, depending on the temperature to which you heat and cool, the amount of graphite you precipitate also changes. So we take advantage of this process to first form a solid solution that exists as a face-centered cubic crystal of palladium and carbon. And as we cool it down, we cool it to the right temperature where we obtain either a monolayer or a bilayer or multi-layer graphene. So in the LEEM movie that you're going to be watching, you will see this nucleation and growth of graphene islands, monolayer graphene islands, which will appear brighter compared to the relatively darker background, which is the palladium surface. And you will also notice these finer changes within the contrast, and that's because of the presence of different rotational domains of graphene on growing on palladium. Okay. So this is the LEEM movie that's obtained while annealing a palladium crystal with a lot of carbon dissolved in the bulk. As we cool it down, the carbon starts segregating on the surface in the form of graphene, and you see the graphene layer growth. If you heat it back up, the carbon redissolves in the surface and goes back into the bulk, and now you have clean palladium surface. And again, this process is repeatable, and so if you heat, you dissolve the graphene, you cool it down, you get graphene back on the surface. And we use this to our advantage to form monolayer graphene. And now I'm going to show the rotational domains that exist when you do an uncontrollable heat and cool of the sample. So these are selected area low energy electron diffraction patterns that are color coded for clarity, obtained from different regions on a given monolayer covered area. And as you can see that, and I won't go into the details of the moire patterns that you observe, but these arrows correspond to, the red arrows correspond to the graphene domain, and the blue arrows correspond to the reference palladium surface, 111 surface. And the magnitude of the arrows and the direction of the arrows correspond to either you have relative orientation with respect to palladium, either as plus 17 degrees or minus 2 degrees, meaning how they're rotated to the left or to the right. Now, the other thing you may have seen here is that these domains look different contrast. And that is because of the amount of electrons that are reflected from the surface, and that depends on the surface structure. And so we can quantify this behavior by using a measurement, what is known as electron reflectivity measurement. And what is done here is that you collect the intensity from a given field of view, and you plot it as a function of the incident electron energy. And so you sweep the electron energy while imaging the same field of view. and watch what you see. So this is the total intensity of this image as a function of electron energy. And as you change, you see the intensity changes. So such a curve is called reflectivity curve. And this change in intensity is a measure of the electronic structure of a given area. Okay. Now here, I have done the same type of measurements, but now in a more localized regions. These three different colors correspond to three different domains of graphene. And for reference, I'm also plotting clean palladium, reflectivity of clean palladium 111 surface. Okay. And what you see here is that each of the domains has slightly different electron reflectivity behavior. Now let me focus on the close to the low energy, so within 5 eV or less. I've just magnified the image intensity, normalized to the initial intensity of the image as a function of electron energy. Now, what I want to tell you here is that initially all the electrons get reflected from the surface, but as you start increasing the energy of the incident electrons, at some point they start interacting with the surface, and there will be a loss in the amount of the intensity because the electrons start getting scattered. And the point at which they start to scatter significantly is a measure of work function. And so in our approach, there are slight variations in this approach, but typically in this normalized intensity, the drop in intensity to about 90%, the energy associated with that is a measure of the surface work function. And because typically one does not know the work function of the filament, you need to find that. And so for that, we can use the reference clean palladium. And once we use that as a reference, we can now have absolute values for the work function. And what you see here is that the work functions of different domains of graphene can be different by up to 15 millielectron volts. So each of the domains with different orientation on palladium has different work function, and that's because from density functional theory calculations, you see that there is a charge transfer from palladium to graphene. And the amount of charge transfer that one obtains depends on the orientation. And one can imagine that if you have two layers, and depending on how each layer is rotated with respect to the other layer, the amount of interaction between carbon and palladium can change. Okay? So that's the reason that you observe this change in intensity. We can do the same.
Suneel,
yes.
May I interrupt you?
Yes.
I have a question. Can you please repeat how have you determined the work function?
Yes.
From in the previous slide. Thank you.
So here, first we collect the image intensity from a given field of view. Yeah. Once you have the image intensities, then you choose the area of interest from which you want to measure the reflectivity curves. Okay. And so if we want this from this red domain, let's say blue domain, then you maybe make a circle or a square and you collect intensities as a function of the electron energy. And then you get this blue curve, and you do the same thing for different areas and you get these curves. Once you have those curves, then what you look for is the 10% drop in the intensity. And so these are normalized to the initial energy's intensity. And so the 10% drop is what the energy that corresponds to that is the work function. But when we plot it, typically the raw data, the energy is the incident electron energy. And here we have the incident electron energy plus the work function of the filament, the LEEM gun filament, which normally we don't know it, but one can get this for that particular measurement if you have a reference. Typically, if you're using a metal, and if you have a clean metal, we can know what the metal's work function is from reference. And so here we take the palladium, and then we assign this the palladium's literature work function value, which of course can have errors in it. And so the absolute energies that we measure has the same error that is associated with the error in measuring the work function of clean metal. But once you have this one, we will then know what the work function of the filament is. And so now we have all these energy values that are plotted here, these are now with the added value of the work function. So then we get the work functions of individual domains.
Okay, thank you very much.
Yes. Okay, so we've, and then this is another experiment where instead of cooling it to moderately a smaller delta T, if you cool it to a higher temperatures or to more cooler temperatures, then you have more carbon segregating onto the surface. And so what you're looking at is multi-layer graphene islands growing, and each of you have this alternating contrast change between alternating layers of graphene. And here is a color-coded image to show you that you have multiple layers of graphene grow selectively, probably at some defect sites on the surface. And once again, you can use reflectivity curves to identify the number of layers you have within a given region. And so these colors, the purple, blue, green, and orange colors here correspond to, yes? Okay, correspond to reflectivity curves from different layers. And this electron reflectivity, the number of bumps you see is mainly because of the interference at these reflection at the interfaces. And so you can measure the number of layers from these reflectivity curves. Okay. And not only that, you can also use the reflectivity data and combine with the LEED patterns, low energy electron diffraction patterns, to get surface work function as a function of layer orientation and layer thickness. Now, there is a lot of information in this plot, so let me walk you through this. All these data correspond to two-layer graphene on palladium. Now, when we grow graphene on palladium, it's growing from the bulk, and so each layer assumes its own orientation without any control. And so this theta 1 corresponds to the orientation of the first layer graphene on palladium. And theta 2 corresponds to the orientation of the second layer graphene on top of the first layer graphene. And here, the phi 2 is the work function of the two-layer graphene, and the phi 1 is the work function of the first layer graphene. So this is the difference in the work functions within the bilayer graphene as a function of relative orientations of the two layers in this bilayer graphene. And the numbers here correspond to the relative orientations of graphene with respect to palladium-111. So as you can see, this is the only one that it has the ideal graphene single crystal orientation. All the other ones, these are misoriented bilayers. Each layer is oriented differently with respect to the other layer. And you see this variation within the work functions by up to 2 eV. Okay, so even within the bilayer, you have a huge variation in the work function. So this is important if you plan to make devices and the relative orientation of the graphene layers affects the device characteristics. Okay. That's the take-home message in here. And also, if you're making graphene metal contacts, the relative orientation of the metal with respect to the graphene layer also can affect the contact resistance. Okay, now let me quickly go through the growth kinetics of these graphene layers. So remember, in this experiments, the graphene grows from the bulk. And what you're looking at is the monolayer graphene growing as the sample is cooled to some temperature. And again, this is a lean movie that's obtained. And we can use these images to quantify the area of graphene domain as a function of annealing time. And this is done in vacuum at about 895 degrees. And you see the this is the total graphene coverage increase as a function of time. So initially there is only palladium surface, and finally there's monolayer graphene covered surface. Okay, now we'll go into the details. So we can pick individual domains and we can measure the areas of these islands as a function of time, and we observe something very interesting. So this is one of the first islands or graphene domains that formed, and that's the green curve here. And this is the later island that formed after 150 seconds. and watch the rate at which this third island or third domain grows. So the islands nucleating at later times grow significantly faster than the domains that nucleated at earlier times. And this is interesting because there is, initially we weren't sure why this would happen. Nevertheless, all these islands, they grow as a function of square of the time, based on which we know that the graphene domains grow. The limiting step during the growth of graphene is the attachment of the atoms to the existing island. So to understand this behavior, we again focused on the reflectivity data. And here I'm going to be presenting reflectivity measurements obtained from an area that's not covered with graphene during the growth of graphene. So this is the already monolayer covered graphene. And here you have some leftover palladium that is eventually going to be covered with graphene. And watch the contrast change. This gets darker and darker with time. And so we can now quantify this behavior. And so by using the electron reflectivity measurements, now we can get the work function within this area. And that's plotted as a function of time. And for reference, this is the monolayer graphene, and this is the work function of monolayer graphene as a function of time. So on the graphene covered area, there is no change in work function. But in the area that is not being yet covered with graphene, there is a significant change in work function. So anytime there is a change in work function, and if you know the environment, which is in vacuum, so there is nothing being added, then it's indicating that there is something changing on the surface. And in this case, we know that there is carbon segregating onto the surface. So there must be a carbon-induced change in the work function. And then it turns out that there is a significant accumulation of carbon. And this behavior is repeatable. So during graphene growth, the work function decreases. And if you start heating it, as the carbon goes back in, the work function recovers almost. And so using this, we then came up with a model for how graphene layers grow. Because the carbon has to segregate from the bulk to form graphene, you have two mechanisms that can contribute to the growth. Either the carbon atoms segregating onto the surface go and attach to an existing graphene island, or the carbon atoms intercalating under an existing layer also contribute to the growth of graphene. And initial stages, it turns out that the attachment of carbon atoms to an existing island is the limiting step. But once it happens that you have more graphene covered surface, we think that there is a dense phase of disordered carbon forms on the surface that prevents or is very limited attachment of these carbon atoms to the existing graphene island. And at later times, it's the intercalated carbon that contributes to the growth of the graphene islands. So that's the graphene layer growth, and hopefully I gave you some idea of what one can do, which you probably already know if you have been doing LEEM, is to use electron reflectivity and electron diffraction in combining with the imaging aspects of LEEM. One can get a very good understanding of the orientation, structure, and property relations in two-dimensional layered materials. And if you also do the dynamics, then you can also get information regarding the mechanisms controlling the growth of graphene layers. Okay, now I'm going to quickly move on to, I have only 10 minutes left, so let's see if I can run through the slides. I wanted to finish all the 2D layers studies today. So we've done similar experiments with the graphene growth on palladium. I will not go through any details. I just want to show you that we can do this and anybody can do this. This is a palladium surface that's exposed to ethylene, and eventually you get graphene. This experiment was done for 8 hours, but you don't need to do it if you increase the pressure. And you can quantify the behavior of how graphene grows. And the nice thing with STM is that you can actually observe the moire in real space images, which in LEEM you cannot obtain. And so from these images, you can then identify the relative orientation of the graphene domains. And we've also done this with, more recently, they use benzene as a source to obtain graphene layers. And this was done with one of the students, Jan Tesharj from SciTech. who came to work at UCLA for 6 months. And so we were able to show that you can have adsorbed layer of benzene that does not form graphene until you heat it up to fairly high temperatures, which is a contrast to what has been reported for benzene, graphene formation using benzene on copper surfaces, which seems to happen at fairly low temperatures. Okay, so that's what I wanted to show you for graphene growth. Now I want to share with you some of our more recent results for hexagonal boron nitride layer growth. Hexagonal boron nitride is isostructural to graphene, but it's insulating. And so it's considered as an ideal dielectric for all two-dimensional layered based devices. And if it's done not properly, you end up also again with polydomain hexagonal boron nitride. And the usual precursors that are used for growing hexagonal boron nitride are borazine, which is a liquid, it's volatile, and or borazane or ammonia borane, which is a solid, and it sublimes at fairly low temperatures around 100 C. And the typical substrates people have used are transition metals, which act as excellent catalysts for the decomposition of borazine. And depending on the type of metal you use, you may obtain commensurate structure or moire patterns. And the surface roughness or the surface corrugation depends on the interaction between the layer and the substrate. And in our experiments, we found that for hexagonal boron nitride on palladium, not only the moire periodicity changes with the orientation of the domain, but the corrugation amplitudes also change. And we also happen to observe similar moire pattern periodicity, but significantly different corrugations, which we interpret as weakly interacting and strongly interacting domain formation. So it's a bifurcation of the domains on palladium 111. Okay, I won't go into those details. I'll quickly wanted to show you how these hexagonal boron nitride layers grow. And here is one example so we start with bare palladium and we introduce borazine. And here are islands of HBN that form, and eventually you form a complete monolayer. And here is a slightly different experiment. So done at different borazine flux and slightly lower temperature. So we start with clean palladium. And once we introduce borazine, we again form a complete monolayer. But the way these monolayers form is different. Let me show it to you in the snapshots. And again, we can measure the growth rates, and also I won't go through these details, but this is visually striking. So let me show it to you. So start with bare palladium, and we end up with complete monolayer of boron nitride. But if you look at the differences in the way the boron nitride forms, here you see island formation on the terraces, followed by complete layer growth. And here you also get islands, but these islands are more fractal, and the attachment occurs preferentially at the step edges. What is more unusual is that the attachment occurs at the up steps, not at the down steps. So this is fairly unconventional growth. But this is the onset of the so-called carpet-like growth that happens in these 2D layered materials. The other unusual aspect is that at lower temperatures, we observe attachment and growth at the step edges, and at higher temperatures, we observe island formation. This is opposite to what is conventionally observed in traditional thin film nucleation and growth kinetics. And so based on these observations, we've formulated and we explain how these layers grow. In both cases, you end up with a carpet. But in one case, under high fluxes of borazine and lower temperatures, you are likely to get a single domain boron nitride. Whereas at the other extreme case, you end up with polydomain boron nitride. Okay? And so there is interesting details regarding how two-dimensional layers grow on these surfaces. And lastly, I have few minutes left, so let me just show you what is nice about these high temperature STM. What you're looking at is a monolayer boron nitride covered palladium surface. and this is being annealed in vacuum. So you're observing the step fluctuations in monolayer hexagonal boron nitride covered palladium, and this is a domain boundary. So you see this defect here, and this is a vacancy island that is inside this. So there is a carpet of hexagonal boron nitride. One of the surprising things, at least for us, is that this moire pattern that you see remains unchanged, meaning the entire surface moves as in unison. So the layer on top sticks to the underlying surface as the underlying surface is fluctuating. And we can also, as you saw in my first portion of the talk, if you have a stiff step, you do not see any fluctuations, and that's the same case here. Whereas if you have a step with lower stiffness, you see these fluctuations. So both these images are obtained at the same temperature with same monolayer boron nitride covered. And so you see that the step stiffness plays a role. And other interesting aspects is that if you have monolayer boron nitride covering the surface, the islands decay at a much slower rate while retaining the same surface orientation. So the layer on top does not get distorted as the palladium islands disappear. Whereas if you have no covering, no monolayer boron nitride, then the islands decay at much faster rate. Okay, so this is a summary of those observations with both atom islands and vacancy islands. On bare palladium, they decay significantly faster than if you have a HBN layer covering the surface. Okay, so I'll stop there, and I just want to point out a couple of things. So why use high temperature STM? Well, one of the advantages is that you can get local atomic scale information. Of course, you can use other complementary techniques, and you should use complementary techniques as and when necessary, because STM alone cannot provide all the information. And some of the challenges that we commonly encounter when you do scanning at higher temperatures is the thermal stability and thermal drift. And yes, it's inevitable, but you can work around it by choosing either lower temperatures or by waiting for longer times. And also, if possible, you can also use LEEM. But again, it's fairly easy to use at different temperatures. And the advantage is that you get to observe phenomena in real time. And that's the key for extracting quantitative information of different types of phenomena. Okay, with that, I'll stop, and thank you for your attention.
So, thank you very much, Suneel, for this nice instructive talk. Yeah, I guess that we have learned a lot, and especially me, I appreciated also the introductory part related to determination of those data on activation energy and barrier heights and so on. Please, are there any questions?
Through a lot in fairly short time. So
yeah, okay. I'm looking at the chat. There is no question, so please. And take it from the. I think maybe Jan Chehal. Jan.
Oh yes, thank you for very nice questions. I have nice lecture. I have a lot of questions. So just I cannot find how to raise my hand electronically.
yes.
And so, for example, one of the questions, because if this boron nitride grow, why it grows on the step edges at higher temperatures? Was it like that? Not lower temperatures. I would expect the opposite.
Yes, yes. So exactly. So we were expecting the opposite as well. And so the reason that we think that is happening, that at lower temperatures, that the layer is growing at the step edges, and at the higher temperatures it grows on the terraces, is because the borazine needs to dissociatively chemisorb on the surface. And the most likely site where it dissociatively chemisorbs readily is at the ascending steps. And that happens readily. But if you increase the temperature, for these dissociation can occur at near equal rates or higher rates on terraces. And that's our assumption. That's a complete hypothesis. We don't have direct proof of it, but that explains our experimental observation.
Okay. So any other question, Jan, or it's all? Maybe I can ask. Yeah,
if there will be other questions, I will ask in the lab.
Okay.
Yeah.
Okay. Maybe just one practical question. I am not too much familiar with that palladium.
Yes.
Crystal. Can you transfer your graphene or HBN from palladium by some bad procedure, like in case of copper and similar metals? So
absolutely, yes. You can transfer it. The only thing is that with copper, nobody cares when you etch it away. Palladium is fairly expensive.
Yeah.
And so unless you deposit really thin films for this purpose, you don't want to use it.
Okay.
When people are happy with copper and nickel, it's yeah.
And how big are your domains of HBN?
We have observed as big as 200 nanometers of sizes, but if we did this experimental in LEEM, maybe we'll have a chance to observe if there is a possibility to grow larger domains.
Okay. Oh, thank you. Thank you. Please, another question.
I would like to ask you just very short question.
Yes.
In case of palladium and carbon, do you expect the same behavior when we will have nickel and carbon?
Almost, yes. So nickel has a little bit higher solubility than palladium, but about the same. The main difference is palladium sublimes and nickel is fairly more stable. So that can affect to some extent the surface diffusivity, but otherwise, yeah, you'll see the same behavior. And nickel also, even if it forms carbides, they're not stable, and palladium doesn't have any carbides. And so, yeah, you will see the same type of single layer growth or multi-layer growth. There is a propensity for carbon to go into the bulk in nickel. Nickel also happens to be a good candidate for dissolving boron nitride. And so it is also possible to dissolve boron nitride and segregate BN on top.
Okay, thank you. Thank you so much.
Okay. Another question.
Is about, I can also follow with this boron nitride. Do you think it would be possible to change to grow some domains of the boron nitride if you increase temperature? For example, in the same case, like you make the coalescence of domains on iridium at high temperatures for graphene.
So
for graphene,
yes,
you can if you on graphene and iridium, if you then increase the temperature to some for like 1400, then you make like single domain graphene on iridium. Would it be possible to do also for boron nitride?
So boron nitride on palladium, I think there's old literature that says it starts reacting and you will break the BN bonds either above 1000 C or so. And so you're limited by that. But what our studies we found is that you're better off trying to optimize the growth conditions to get larger domains than trying to anneal. Annealing, for BN to move, you really need high temperatures, and typically BN will start reacting with pretty much all metals by that time. Yes.
That's concerning that spiral step motion. Can you somehow switch it on purpose and switch off, and then to go to another type of growth, or because I don't understand it. Yeah, it's just maybe it's
so
question is not too much.
Spiral steps are the first ones to grow, even if you have, let's say you're depositing material intentionally.
Yeah.
A spiral step is the first place you will have attachment compared to on flat terraces. And so the spirals will grow preferentially. And in our experiments, we are not supplying any material to deposit. And even in that case, there is this spiral motion because the atoms are moving away from the steps into the bulk. And so it's presumably because there are titanium vacancies and they're moving back into the bulk. And that gives rise to this spiral motion that you saw in the videos.
Mm-hmm. Okay, thank you. Have you already tried to measure transport properties of your products? Let's say either graphene or another one.
No, we never did this. These so anytime we do these experiments in STM, these are 2 millimeter by 10 millimeter samples, and yeah, we never tried to do any transport.
Yeah. And this is on that expensive crystal. Yeah. Okay. So you don't.
No, these were done with thin films. Yeah. So we don't use a bulk crystal. It turns out that the bulk crystal doesn't matter what size you choose. If you try to buy it, it's about the same price. So we deposit thin films on sapphire by sputtering, and we get highly single crystalline domains of palladium.
Okay. So okay, seems that there are no other questions. So thank you very much.
Thank you.
And